Hello class, today we are going to look at bisectors of triangles. And what this isn't so much bisectors of triangles, but it's angle bisector and perpendicular bisectors when we put those in triangles. Alright, so we're going to take some stuff we already know and see how does this work inside a triangle. So first we have angle bisectors, and before we get into that too much, I want to remind you how we construct an angle bisector. Remember with the compass here? So, okay, let's grab the compass. Move it up here, just make it a little bit. Bring that in a little bit. Remember, you make a little arc across the angle. It's not picking things up like it's supposed to. There we go. Then you center the compass on one of these intersections. Make a little arc centered on the other intersection. Bring it over here and make an intersection right there. And then we're going to come over here and get a little line. Draw it from point A through this intersection, and this is an angle bisector. All right. Now, if you'll notice, when we do this, this point right here is the same distance from both of these intersections, right? It's the same distance from both sides of the angle. And so I want to look at that real quickly. So here we go. I have an angle here. I've used the angle bisector tool on this software here. So notice, let's see here, there we go. When I move the angle, the line H stays as an angle bisector, okay? Now, we're going to take a look at some stuff. Here's my perpendicular line. So if you'll recall, distance is always a perpendicular distance to whatever it is you're looking for. So I want the distance right here. So I got this perpendicular line, and here's distance. I want to find the distance from point D to line F, and I also want to find the distance from point D to line G. And I'm not going to draw that line in there. Just know that it is always perpendicular. So just want to do that one. What do you notice about these two distances? Yeah, they're the same all the way down here to 10 decimal places. And as I change my angle, those distances stay the same, don't they? If I move my point, the distances stay the same. So this is very important. This is very useful stuff. So what we can say about this is that any point on an angle bisector is equidistant. It's the same distance to the sides of the angle. All right. So now let's take a look at that inside a triangle. So let me get another segment here. I'm going to make a triangle real quick. There. So now I have a triangle, and let's get angle bisectors for those other two angles. So we want to bisect angle B, and we want to bisect angle C. Now, if you'll notice, let's move that out of the way. All three of the angle bisectors intersect at the same point, don't they? When you have three lines come together at the same point, we call that a point of concurrency. Okay, so this is the point of concurrency. And let's just put D right there on that. And let's see if this will do it the way I want to do it. Nope, D's not staying there. So let's get rid of D and let's just make a new D. Give me a point. There we go. We've got a new point D. And as we saw a minute ago, the distance from any point on the angle bisector is going to be the same distance to the sides of the angle. Well, since this is the angle bisector for all three of the angles, that means it is the same distance to the sides of all three of the angles. So it's the same distance to the sides of the triangle. And notice point D is the same distance to all three sides. Now, point D has a name. We give it a special name since it is kind of a special point. It's where all these come together. We call it the incenter. All right? And notice that no matter how I move my triangle around, all of those distances stay the same. All right? Notice this is not the distance to the angles, right? Because you can see quite clearly D is quite a bit closer to angle C than it is to angle B, right? This is the distance to the sides. Now, one of the reasons we call this the incenter is because, hold on a second, I need to get that perpendicular line back. There we go. The reason this is called the incenter is because it is the center of a line, the center of a circle that is drawn inside the triangle. All right, so let me move that distance. So here we have a circle drawn inside the triangle. No matter how I move my triangle around, that circle is always touching the sides. This is called inscribed. So the incenter is the center of an inscribed circle. And as you remember, all the radii of a circle are the same length, and that's this distance here. That's why it's the same distance all the way around. So, a couple of things we can write down here. Let me get me a triangle. Triangle. There we go. So all three angle bisectors intersect at the incenter. Right there, that's the incenter. And it is equidistant to all three sides. It's the same distance to all the sides. And also, that is called the point of concurrency. So if you need to spell that, that's how that's spelled. All right, the point of concurrency. And again, we call it the incenter because it is the center of a circle that is drawn inside the triangle, inscribed circle. All right. So you see that is an inscribed circle. Right there. Inscribed circle. So the incenter is inside the inscribed circle and it just touches the sides. So it's equidistant to the sides. That's how I remember that, because I remember the incenter is that circle on the inside, so it's touching the sides. All right. Now, let's take a look at the perpendicular bisector. Again, I want to remember how we construct that perpendicular bisector because it's going to show us some interesting things here. So we start at there and we draw an arc going below and above. That's probably too big, like that. And then we go to the other side and we want to get an intersection across that. Two intersections there. And then we're going to draw us a line connecting those dots. Okay, now, notice when I drew this, I used my compass, and this point is the same distance to point B as it is to point A, right? Same distance right there as it is to B. Same distance to A as B. So let's take a look at that. Okay, so here I've used the perpendicular bisector tool. So to bisect segment AB, notice when I move it, it stays there in the middle, always perpendicular. And again, we're going to look at distances. So I just want a point here. Let's just take a point right there. Why not? And where's my distance tool? There we go. So the distance from point C to point A, the distance from point C to point B, and notice that those are exactly the same. Same distance to CA as CB. And no matter where I move point C, notice those distances stay the same. I can move it to the other side. I can move A and B, change that length there, and notice those distances are always equal to each other. All right, so let's take a little bit of notes on that. So I'm going to write that down real quick. I want to note that any endpoint, or any point on the perpendicular bisector is going to be equidistant to the endpoint. It's going to be the same distance there. All right. So let's take a look at what that looks like inside a triangle. So let's draw a triangle here. Extend that out so, and then connect those. I don't want it going through that same point over there. All right. So now where's my perpendicular bisector tool? Right there it is. So let's bisect DA. Let's bisect BD. And notice that once again, all of these points, all of these lines are coming together at a single point. Again, a point of concurrency is what that's called. All right. Now, looking at this, is this point of concurrency, which we are going to call the circumcenter. For the perpendicular bisectors, the point of concurrency is the circumcenter. Notice this is not going to be equidistant from the sides, is it? Notice it's a lot closer to side DB than it is to side DA. But we said the perpendicular bisector was equidistant from the endpoints of the segment. Well, in this case, the endpoints of the segment are the vertices of our triangle. So let's come down here, and where's my distance? There we go. So the distance from C to A, the distance from C to D, the distance from C to B, and notice all three of those are the same. So the circumcenter is the same distance, whoa, that was weird. Okay, the circumcenter is the same distance to all of the vertices, not to all of the sides. But do notice, the circumcenter here is outside of the triangle, isn't it? That's weird. So we have a center for the triangle that is not actually in the triangle. All right? But at all times, it is equidistant to the angles. All right? All of these distances to the angles are the same. So let's take a look at this since it's not inside the triangle. Let's see what kind of triangle will have the circumcenter inside the triangle. So let's move this around a bit. Try to keep it inside there. It's still inside. Still inside the triangle, about to go outside. Still inside the triangle over here. Notice all of these places where, oh, it went outside, so that's not good. Here, all of these places where I have it inside the triangles are acute. Right? They are all acute triangles. So let's see, let's get it outside the triangle. Let's see that. There we go, outside the triangle. Notice what kind of triangle do we have now? Yeah, now we have an obtuse triangle, and as long as it stays obtuse, it stays outside. But if I bring it acute, it came back inside, right? So what would a right triangle look like? Let's see, let's measure this angle so I can make sure that it's a right angle. Let's make the angle be a right angle. Okay, so let's see, and back to my moving tool. There we go. And let's see, get it right. Oh, too far. Pretty close. It's not getting quite to a right angle. I'm getting a little bit. So there we go. We're pretty close to a right angle. And where is the circumcenter now? Yeah, now the circumcenter is right there on the triangle. So when it's a right triangle, it will be on the triangle. If it's an acute triangle, the circumcenter is on the inside. If it's obtuse, the circumcenter is on the outside. Now, one thing really quick. The incenter was the center of a circle drawn inside the triangle called an inscribed circle. Notice the circumcenter is the center of a circle drawn around the triangle. Circum means around. To circumvent something means to get around it so that it doesn't happen. To circumnavigate means to go around the globe on a boat. So to circumscribe, which is what this is called, circumscribe means to draw around. So that's what this is. This is a circle drawn around the triangle. All right, so let's get back over here where we can take some notes. Let's move that out of the way. Don't need that. Okay, so all three perpendicular bisectors intersect at the circumcenter, which is equidistant to all three vertices. And remember that for an acute triangle, it will be on the inside. For an obtuse, For an obtuse triangle, the circumcenter will be on the outside. And for a right triangle, the circumcenter will be on the triangle. And specifically, it will be at the midpoint of the hypotenuse, right there. That is where the circumcenter is. This is the intersection of the perpendicular bisectors, which was equidistant to the vertices. All right, so we're going to look at a couple of questions really quickly. So, in triangle ABC, is D the incenter or the circumcenter? Well, looking at this, we've got a lot of stuff here. Notice that the angles here are congruent. These angles are congruent to each other. Those angles are congruent to each other. So we have angle bisectors here. And since it's angle bisectors, this is going to be the incenter. So which other segments do we know the length of? Do we know something else that's 10, something else that's 7, something else that's 8? That's the question, really, what it's asking here. And since this is the incenter, that means it is equidistant to the sides. So all of these lines that are perpendicular to the sides, those segments are going to be the same. And so we know the length of ED is 7, and we know that the length of DF is 7 because it's going to the sides. All right. So take a look at this one. Now, is D the circumcenter or the incenter? Well, notice what's marked congruent. It's not these angles anymore. Now it's the sides. So this is going through the middle of the side. So this is a bisector. And it's perpendicular. See the right angles there? So these are perpendicular bisectors, which means this is going to be the circumcenter because we're using perpendicular bisectors. Okay. So now what other segments do we know? Do we know something else that's congruent to the 6, something else that's congruent to the 8? Well, we know something that is congruent to the 8. The circumcenter is equidistant to the vertices. And so since 8, that's the distance from the center to the vertice, to the vertex B, that's going to be the center to all of the vertices. So AD is going to be 8, and CD is also going to be 8. All right. Now, this actually does have some application, some real-world application here. For example, if you want to place a sprinkler in your yard so that the edge, it gets to the edge of your yard, but it doesn't get your sidewalks wet, where should you put your sprinkler? Incenter or circumcenter? Well, let's see here. We want to go all the way to the edge without actually getting over the sidewalk, right? So which one is the same distance to all the edges, all of the sides? Well, that is going to be the incenter right there. So that right there is where you're going to put your sprinkler. Now, of course, you got your corners here aren't going to get watered, but you got to figure out something else for that. But this is how you put it right there. All right. Another thing you can do with this, let's say you want to put your dog on a leash out in your yard, and you want to make sure that the dog can reach the door, the doghouse, and the shade tree because you don't have a fence. So you got to leash it down somewhere. Where are you going to stake your leash? At the incenter of these 3 points or at the circumcenter of these 3 points? Well, let's see. These are 3 points on a triangle. These are the corners, right? So which one is the same distance to all the corners? That is the circumcenter right there. So, for example, let's just so you can see this. And that's going to be right there, same distance to all the sides. I don't know why I have 2 compasses now, whatever. Same distance to all the corners, the circumcenter. Right? So, just a reminder, real quick. Perpendicular bisectors intersect at the circumcenter, that's called the point of concurrency, and it is made from the perpendicular bisectors, and it is equidistant to all of the corners. Sometimes it's on the inside, sometimes it's on the outside. Angle bisectors, on the other hand, intersect at the incenter, which is the center of an inscribed circle drawn inside of it, and it is going to be equidistant to all of the sides. So, there it is. Hope you found that useful, and I will see you in the next video.